Welcome back, everyone, to the coaching seminar on differential algebra. Our first speaker this semester is Matthew Babbitt, who will give us a presentation on summability of elliptic functions via residues.
Thank you, Dr. Roberts. I would like to thank everyone here at the Colchin Seminar for having me. And I would also like to thank the National Science Foundation, which actually helped support this research. This is joint work between me and my PhD supervisor, Dr. Carlos Areche. Uh, and in fact, what you see will be in my thesis that I am writing at the very moment. All right. So we are going to be concerned about summability of elliptic functions via residues. These aren't necessarily the residues from complex analysis. These are a different technology that have been seeing more use recently. So just some motivating examples that are like really easy to fit on an entire slide. If we if we're considering the field of rational functions over, say, the complex numbers, right? Each of those functions has a unique partial fraction decomposition. So you express it as a polynomial plus a sum of a bunch of terms, a coefficient divided by some exponential of a linear, right? Where the denominators form the uh, factorization of the denominator of f of x, right? You can get a lot of information just by knowing what the coefficients are, and you can determine a lot of information from of f from those coefficients. So, for instance, if you want to determine if f has an antiderivative, so f is rationally integrable, this happens if and only if the coefficients of uh, x minus alpha to the -1 all vanish. And we can call those the residues of our function of order 1, right? And it's remarkable that you only need to look at those numbers to get that. And so similarly, work from Chen and Singer in 2012 answers a similar question for rational summability. Instead of saying if f has an antiderivative, we are looking for if f can be expressed as a difference g of x plus 1 minus g of x for some rational function g. And this is a bit harder, but they show that you can still accomplish this problem just by looking at the numerators of the partial fraction decomposition. What you do is you consider every z orbit of the complex plane, and then you sum over each individual order those numerators. And that gives you the discrete residue over that orbit of order k of the function. And it turns out that a function is rationally summable if and only if all of the discrete residues vanish. So the discrete residues form an obstruction to rational summability. All right. And uh, more recent work has accomplished similar things for Q discrete residues, rather the Q, uh, uh, the Q difference, Q differences and molar differences. And uh, you can define different sorts of residues in those cases to accomplish to create an obstruction for summability. And they get more complicated as you go on. I'm actually interested in the problem of summability of elliptic functions. And this plays into the study of difference equations over elliptic curves. uh, and so a real brief introduction to what we can do with those sorts of things, like why we would care. There have been some really fun applications in combinatorics, right? Like suppose you're walking in the first quadrant and you're only allowed to take a certain prescribed set of steps, right? Like maybe you're not allowed to like move in all the directions that a king can. Maybe you can only go up or right or down left. Uh, then it's an issue. Then it's an interesting problem to see how many ways you can get to a particular point in the quadrant in a certain number of moves. Uh, so a natural way of modeling that is a generating function. And it turns out that a certain segment of the generating function can be formulated as an elliptic function, which satisfies a difference equation, right? Another application is in mathematical physics, where you have these elliptic hypergeometric functions studied by Spiridonov, right? And they're expressed as these huge complicated things, but it turns out that Spiridonov showed that these satisfy a difference equation over elliptic curves, right? So I'm interested in difference equations over elliptic curves and more specifically their summability. And it's interesting that they have all these uh, applications, and I'm very eager to see where this will lead. Okay, so I'm sure that all of you know uh, are very familiar with elliptic curves, but just to give a brief whirlwind introduction, from two different viewpoints, we're going to be handling the analytic viewpoints as well as a more algebraic one later on. From complex analysis, if you have a two-dimensional lattice lambda in the complex plane, the field of lambda elliptic functions is the field of functions that is lambda periodic for every lattice point lambda. These are doubly periodic meromorphic functions. Okay. The behavior of any one of these functions is determined by just looking at its behavior on one of the parallelograms that is formed by this lattice, right? In the quotient space C mod lambda. So you can actually view these doubly periodic meromorphic functions as functions on that quotient space C mod lambda. And so we call that space the elliptic curve with respect to this lattice lambda. And we call the meromorphic functions on it elliptic functions. And these functions satisfy a lot of nice properties, like this. They play this nice balancing game with the zeros and the poles having to be equal in number. And they also need to have equal sum on the elliptic curve. And what's more is that non-constant elliptic functions, it turns out that you can't have a non-constant elliptic function with exactly one pole. It turns out that they must have at least two poles in the elliptic function. Okay. There are some really nice examples of elliptic functions. Like this is the prototypical one, the Weierstrass P function, right? And it's defined by this convergent series defined in terms of all the lattice periods. And this P function satisfies a really nice differential equation. And really, it is a polynomial relationship in terms of P and its derivative P prime. And even more exciting is that the field of elliptic functions is actually generated by P and P prime, right? Like every elliptic function can be expressed as a rational function of P and P prime. Now, there are actually other Weierstrass functions. The zeta function is also defined in terms of this convergent series, this second one, but it is not actually elliptic, right? It has relationships to elliptic functions, though, right? Like the derivative is elliptic and any difference is elliptic. And this zeta function is actually going to show up in a lot of our computations from the algebraic viewpoint, from the analytic viewpoint, sorry. Okay, so that is a very brief introduction to elliptic functions and elliptic curves. So how do we define a difference equation on them? Well, for a fixed shift S in the plane, in the complex plane, that isn't an element of Q times lambda. That is to say that no non-zero integer multiples of S are in lambda. We call the projection S bar onto the elliptic curve a non-torsion point. Our shift automorphism on the field of elliptic functions is defined by taking an elliptic function and shifting the input by S. So f of z goes to f of z plus s. And this does, in fact, define an automorphism on the field of elliptic functions. And with this automorphism, we can then define a linear difference equation over the elliptic curve with respect to this particular automorphism. And it is an equation of this form, where the first and last coefficients are non-vanishing, right? It is a linear combination of a formal variable y with its n successive shifts. And then finally, we say that a function that is an elliptic function is called elliptically summable if there exists a solution to this particular difference equation that is itself elliptic. Okay? So I'm interested in these, but really what I do is differential Galois theory over of linear difference equations over elliptic curves. And it turns out that elliptic summability is a key subproblem in computing these differential Galois groups, which is why I'm interested in determining elliptic summability. Okay, so this is the goal. We want a complete obstruction to elliptic summability, just like the discrete residues in the rational case being an obstruction to rational summability by Chen-Singer. Uh, Unfortunately, elliptic functions are complicated, right? Like in the rational case, we had partial fraction decompositions to utilize, but elliptic functions don't really have those, especially because partial fraction decompositions are expressed in terms of these 1 over z minus alpha things, right? Those have exactly one pole. And non-constant elliptic functions must have at least two poles, which prevents us from directly just elliptifying the Chen-Singer strategy. So it's not so easy to jump from the rational to the elliptic case. But previously, Dreyfus, Hardwan, Rock, and Singer did a bunch of work in this direction, and they get a partial obstruction to elliptic summability, and that overcomes all of these obstacles, which is great. And so our contribution is we're going to complete this obstruction to elliptic summability. Okay? All right, so that is the goal for today. We're going to first provide the analytic version of the story. And this is a reinterpretation of what Dreyfus, Hardwan, Rock, and Singer did back in 2018. They formulated it algebraically, but their work also applies in the analytic case. And so we can formulate it here as well. So for an elliptic function, you can find the principal part of its local expansion at any complex number alpha, right? And you get these numerators once again. This isn't quite a partial fraction decomposition. It's like the local version of it. And we then want to sum over all the orbits of the shift function, right? The shift automorphism as opposed to the z orbits on C, right? So we're going to choose a representative of each orbit, C mod lambda mod zs, right? So this is really the elliptic curve modding out by this shift. And then Dreyfus, Hardwan, Mark, and Singer define the analytic orbital residue of the elliptic function at the orbit of order k to be the sum of these numerators over this orbit at the order k. And what they show is that if f is elliptically summable, then all the orbital residues vanish. Great. They also show that if all the orbital residues vanish, then f is nearly elliptically summable. So what does that mean exactly in the analytic case? What they show is that there exists in you can reduce f by this summable elliptic function, gz plus s minus gz, and the remainder can be expressed in terms of zeta functions, right? It is this constant term r0 plus this difference of zeta z plus s minus zeta z, which is in fact elliptic, right? It's not that hard to show that if you have this reduction of f, then f is elliptically summable if and only if the remainder, r0 and r1, both vanish. Okay? So what we want to do is we want to find a definition for these constants, kind of like the orbital residues, that lets us determine exactly when they vanish given a function f. Now we don't want these to depend on a g of z, right? Like we don't want to have to reduce f through a bunch of algebra in order to calculate R0 and R1, right? We want to skip that entire process. But also, we want to be able to define these R0 and R1 in the case when the orbital residues may not necessarily vanish, right? So again, we want to be able to see them from the level of F without having to do any work finding the orbital residues in the first place, right? So we'll be able to find them in parallel with the orbital residues. So this is the goal for what we're doing. There does not exist a partial fraction decomposition of elliptic functions, but there's something that's close enough. We're once again going to be choosing representatives of all of the orbits of the shift on the torus, on the elliptic curve E lambda, right? We're going to call these choices an analytic pinning. And it turns out that given an analytic pinning, you can express f of z entirely in terms of zeta functions, right? In fact, uniquely given the pinning. So given a pinning, there exist unique constants such that f of z is the constant c0 psi f plus this linear combination of all the zetas at all the orbits anchored at each element of the pinning and their derivatives. All right, this is a classical result, and it is seldom recorded. We found exactly one source of this so far, and we're going to call this the zeta expansion of our elliptic function f relative to the analytic pinning. Okay, so with this analytic pinning, what we can do is we can go calculate that reduction of f by summable functions and use that to define two new pan-orbital residues, right? So we have these orbital residues that we can see directly from the zeta expansion, right? Not just from the local expansion of f, but we can also get it from the zeta expansion. Now, relative to this zeta expansion, we're going to compute these analytic pan-orbital residues. Once again, we're combining all the order 1 residues of f in a rather twisted way, right? There's this new factor of n in each of the terms. So the choice of analytic pinning does matter for the computation of this pan-orbital residue. And then the 0th order residue is the leftover constant term, C0 psi of f. Given these pan-orbital residues, that actually completes the obstruction for elliptic summability. An elliptic function is summable if and only if all the orbital residues and both pan-orbital residues vanish. Now, I'd like to actually stress that the way that we showed this is it really relies on the proof of Dreyfus, Hardwell, Rock, and Singer's result on orbital residues, right? They proved their result on orbital residues by making this reduction on elliptic functions to get that the orbital residues vanishing is necessary. The way that we prove this is we carried out that same reduction that they had and kept track of it explicitly using zeta functions. Okay, so this relies very much on their work. But all right, this completes the story in the analytic case, which is great. But how do we make a computer do it, right? Presumably, we would want to be able to compute these sorts of things, right? The pan-orbital residue isn't so bad. It's from the zeta expression, but it's also from the local expansions of your function. But C0 psi of f is a mystery, right? Like, in order to find this C0, you take your elliptic function f, you find the zeta expansion, and then subtract all the zetas from it. And how do you make a computer do that and spit out a constant? Like, I actually don't have ideas for this. The best I could imagine is like estimating everything, but summability isn't an estimation problem, it's an exact problem. Your function is summable or it's not. So the analytic story isn't quite enough to get this in a computable state. But it does give us a lot of intuition for how to handle the algebraic context. So now we're going to switch gears to the algebraic context, and we're actually going to be able to see uh, the exact results that Dreyfus, Hardwell, and Singer did back in 2018, and how we can redefine pan-orbital residues in that context to solve this problem in the algebraic case. Okay. So once again, we're going to have a whirlwind tour of elliptic curves and elliptic functions. And this time we're going to be working over a field K, algebraically closed and of characteristic 0, right? If we're working algebraically, then anything we do on C should work on K, right? So we're going to make K much more general here. We're going to define, well, rather, an elliptic curve over the field K is defined as the projective curve corresponding to this homogeneous polynomial, where G2 and G3 are constants in the field K. And we can actually, with great effort, reformulate the previous difference structure. This elliptic curve is equipped with this fun group law, really famous. It's on the covers of all the elliptic curves textbooks, right? And then given a non-torsion point on your elliptic curve, we're going to consider the shift automorphism that adds S using this group law to the argument of the function f. And this once again defines an automorphism of the field of elliptic functions on E, and in particular, rational functions on E. When I say rational functions, I do mean that very explicitly. The field of elliptic functions is isomorphic to the field of rational functions in two variables x and y, subject to this cubic equation relation, right? And notice that this actually looks exactly like the polynomial relationship between the Weierstrass P function and its derivative. That's actually a special case of the algebraic viewpoint, right? Now, and if you go look at the shift automorphism, it is in fact these maps just defined in terms of rational functions. So we are really dealing with a field of rational functions. It's just that now we're dealing with it over a curve of genus 1, the elliptic curve, as opposed to a curve of genus 0, like the complex plane. All right. And then in this setting, like elliptic summability is defined exactly like before. We want to solve the difference equation f equals tau g minus g, and f is summable if and only if there exists an elliptic solution to this equation. Okay, so this is the algebraic setting in which we are working. So now we're actually ready to start talking about the exact statement of the result of Dreyfus, Hardwell, and Singer. Once again, they described it in terms of local expansions of our elliptic function, right? And this is just what happened in the analytic story, right? There needs to be some greater structure to the local expansions we take, though. Each expansion is done with respect to a local uniformizer, and we need to select those local uniformizers to respect the shift automorphism. So we choose a compatible system of local uniformizers such that the shift of UP at a point P is U of P minus S. Okay. And then once we have this compatible system of local uniformizers, we can take all of these local expansions again, and they are unique. So we can take these coefficients of these powers of local uniformizers. And these are the numbers that we're going to use to define our residues. Now, in the analytic story, we were taking the local expansions in terms of local uniformizers on the universal covering space, right? Z minus alpha is a local uniformizer on C, not C mod lambda, right? They're clearly shift compatible, but even if they're not elliptic functions, we were still able to use that local data from uh, these uniformizers on the covering space. Here, we don't have a covering space to work with, right? Especially if we're dealing with a general algebraically closed field. We don't have access to the analytic structure of the complex plane. So we need to be very careful here. And so this is the technology that Dreyfus, Hardwan, Rock, and Singer set up in order to define residues in the elliptic setting, in the elliptic case. Now, this is a summary of what they did. This is exactly what they did. So given this set of local uniformizers and these local expansions of all the uniformizers, we can define these orbital residues analogously as before. We're gonna take a representative in each orbit and then sum over that orbit at a particular order k, and this defines the u orbital residue of the elliptic function f, right? Just as before. And the exact result that they showed is that if f is elliptically summable, then the orbital residues all vanish. And on the other hand, if the orbital residues all vanish, the function is nearly elliptically summable. Now, what does that mean? The way that it worked in the analytic story is we were able to express it in terms of zeta functions, right? But zeta functions were functions on C, not C mod lambda, right? They're on the covering space, and we don't have access to that. So we need some more technology to talk about what this means. So we need to talk about a little algebraic geometry. So an effective divisor, D on a curve E, particularly an elliptic curve, is just a formal sum of points. It's effective if all the coefficients are non-negative. Okay, and divisors are defined to have finite support. So almost every NP vanishes. And then we can define the degree of a divisor to be the sum of these coefficients. So this technology is really useful if we want to describe the collection of functions with particular divisors, right? Or a particular set of prescribed poles. And these are, and the way that we can describe these is with Riemann-Roch spaces. So for given any divisor D, L of D is going to be the K vector space of elliptic functions such that the function has a pole of order at most NP at any particular point P. So the Riemann-Roch space is saying here is a divisor. Here is where you're allowed to have poles. You can only have poles of this many order there. And then the Riemann-Roch theorem is actually a theorem about the dimensions of these Riemann-Roch spaces. Now, what's written here is not the Riemann-Roch theorem. The Riemann-Roch theorem is actually much more general than this. But what we have here is a version that works for effective divisors on an elliptic curve E. In particular, the curve E as genus 1, which is synonymous with it being an elliptic curve. And in this case, we can actually show that the dimension of LD is precisely the degree of the divisor D. Okay, so the dimension of the vector space of these, the dimension of this Riemann-Roch vector space is exactly determined by the degree of the divisor, which is really helpful for constructing functions with particular divisors. Okay, so with this technology, we can now talk about the exact formulation of the orbital residue results. What it means for a function to be nearly elliptically summable in this case is there exists a reduction by a summable part, tau g minus g, such that after the reduction, the remainder phi is in this Riemann-Roch space, O plus S. So it can have one pole at the base point O of the elliptic curve, and it can have one pole at the shift S, defining the shift automorphism. Okay, so the remainder has at most two poles at two really particular spots. And once again, it's not too hard to show that F is summable if and only if this remainder vanishes. So once again, our goal is to define certain constants that let us detect whenever this function phi vanishes. Okay, and we will need to define these once again in the case when the orbital residues don't necessarily vanish, right? Okay. So how do we do that? Well, before we had analytic pinnings. Here, we need a bit more information. So once again, we need a compatible system of local uniformizers, right? Like in order to even work with anything, we need a choice of representatives. We're going to use a distinguished orbit as well. And we're going to call a pinning F admissible if the function doesn't have any poles on the distinguished orbit and it is non-singular to the left of all the representatives of the orbits. So F being non-singular at Q omega minus NS when S is non-negative. Okay. And incidentally, if you want to make an algebraic pinning that is F admissible for a collection of functions, this is possible because any elliptic function has only finitely many poles. So just aggregate your functions and then find an algebraic pinning that is F admissible for all of them. We can do that. Okay, given this algebraic pinning, we can construct a bunch of functions that mirror the uses of the Weierstrass zeta function in terms of this algebraic pinning. Now this is done very carefully using the Riemann-Roch theorem actually, so that we have functions with very particular poles and very particular local expansions at those poles. And then if we get all this machinery, hold our breaths, and then do the reduction again very carefully, we once again are able to define pan-orbital residues in these cases, in the algebraic setting. So the pan-orbital residue of order 1 is this sum, once again twisted by this factor n. So it actually looks quite similar to the analytic pan-orbital residue. The 0th order pan-orbital residue has a much larger expression. And with these things, we are now able to show that an elliptic function f is summable if and only if all the orbital residues and both pan-orbital residues vanish. This is the complete obstruction to elliptic summability. Now the 0th pan-orbital residue looks really dicey, but actually it's somehow more manageable than the one in the analytic setting, right? In the analytic setting, you're required to find the C0 psi of f, and you do that by taking your elliptic function and subtracting all the zeta functions and working really hard to find that constant. Here, we have all of these functions. We have a really good sense of what they are. So I think we have a much better chance of computing this function. Especially since everything is now explicit instead of like in terms of like things we need to go find a priori. All right. So this is the complete obstruction for elliptic summability. Now there are a few things that I'd like to do with this thing. So uh, this is all computable in principle, right? But we need to go find a way to actually implement it onto a computer. And this is something I have extremely little experience with. Uh, but I get the sense that a lot of people do a lot of like computations with elliptic curves. Um, and it's I believe it is all done in the algebraic setting. So what we've got is, I believe, really close to actually computable. We would just need to go implement it somehow. I'm not entirely sure about the process yet. Uh, this summability obstruction actually is part of a larger program that I had started at the beginning of my doctoral studies, where my goal was to compute differential Galois groups of low order or even diagonal linear difference equations or systems of linear difference equations over elliptic curves. And now that we have this obstruction for summability, uh, we are able to do this now. And this is something that is uh, on my radar to follow up with. Uh, Also, there's a third language for elliptic curves called Tate curves, and these are uh, curves of the form C star mod q to the z are Tate curves. So this is the uh, you take the multiplicative complex plane now, and you mod out by the action of multiplying by q, where q is not a root of unity, and this is a Tate curve. And we can define summability in this context. And I'd like to see an obstruction to when functions on this Tate curve are summable. Uh, and this is something that we've been working on and we're almost done. It turns out that the analytic case gives a lot of intuition for this as well. So this is on the horizon and it's in the oven. We just need to finish baking it. All right. Uh, and with that, uh, yeah, that's all I have. Thank you very much.
Thank you very much, Matthew, for this very interesting and very clear presentation. Are there any remarks or questions? Please just unmute yourself or write in the chat. So any questions for Matthew? So in your future work, you mentioned these items. Do you already know which of these items is up next in your work?
Actually, the Tate curves is like on the precipice of being
Yeah,
done.
yeah.
And this is actually something that I was hoping to get into the thesis, but the thesis is due in 2 hours.
Oh, okay.
So I don't think this is going to happen. But we've got a bunch of preliminary computations done. We got the Stirling numbers to pop out. I'm very excited. I can't believe we tied the Stirling numbers into it. It's really fun. We got the Stirling numbers of both kinds because they end up being like a change of basis kind of deal, right? So I'm very excited to like get all of that pinned down and get that third formulation done and ready to go. And it will probably appear in a paper as opposed to a thesis.
Very nice. Are there other questions from the audience?
In fact,
This is, yeah.
I have to run really soon, but I would love to make one quick comment if Matthew could go back to the previous slide.
Uh, this,
Yeah. So in the first paranorbital residue on top, this like a d sub k xi that show up there. When we're about to finish, like Matthew said, the state curve version of these things, and the Stirling numbers of I forget either the first or second kind show up in place of these D coefficients. So to me, there's some mystery here that I don't know how to explain yet, but I'm really excited to get all the details sorted out and then show it to people. So.
Any more questions or remarks? If this is not the case, then we wish you success with submitting your thesis in 2 hours or before, and of course also for your defense, etc. And we would like to thank you again for your very nice talk.
Thank you very much. And thank you for having me. This has been fun.
Thank you.
Mhm.
And I think the next talk in the seminar is coming up at the end of the month, if I remember well. So see you all later. Thank you very much.
Take care.